that I'm conducting is on building a scalable architecture for web applications. And I'm actually going to cover across these 60 minutes a pretty interesting transition of how, how you'd start off with a very simplistic deployment in terms of an architecture and take it all the way to an architecture that can support millions of users, is infinitely scalable, can support as many transactions as you want, and is the common lingo that we use, high availability and resilient and so on and so forth. This is sort of a rough agenda, starting off with why scalability is important, then covering some of the variables and factors, and then really the crux of the presentation starts where we actually build our own scalable architecture in incremental steps. And you'll hear these terms across the presentation, vertical, some of you might have heard them already in applications that you're building today. Vertical scaling, vertical partitioning, horizontal scaling and horizontal partitioning, and what they mean, what are the ramifications of each of them. I'm going to cover load balancing and various techniques for horizontal scaling and horizontal partitioning, etc. And then sort of end with some tips and platform considerations, etc. So to start with, why is scalability important in a Web 2.0 world? Some of is one way to look at it is that what's a scalable architecture presentation doing a rich Web 2.0 conference. Another way to look at it is if you look at Web 2.0 applications, the successful ones like Facebook, Flickr, any of the successful applications that some of you guys might be building, scalability is actually the one common attribute and aspect across all these applications. Some of them might be built in Flex, some of them might be built in Ajax, but all of them need to have a scalable web architecture, a scalable backend architecture, a scalable deployment to be able to actually service the kind of transactions, the kind of users that you're looking at. Viral marketing can result in instant successes. And if you look at many of the Web 2.0 experiences and technologies and paradigms, if you look at RSS, Ajax, etc., they generally use XML as a base protocol, which, as we all know, XML typically has more metadata than data, automatically results in greater bandwidth consumption, and therefore, greater amount of transfer, greater amount of load on web servers or application servers, etc. Many of the paradigms, use protocols like RSS or Comet is sort of a push-based version of HTTP, but use HTTP as an underlying protocol. And HTTP is a pull-based protocol. It's a polling-based protocol. Typically, you'll end up with numerous number of requests hitting your server for data that might events that might take place once in a while. So you're looking at any sort of Web 2.0 application that sort of uses these paradigms, uses these technologies, is going to require a scalable architecture. Even if you look at the dynamic language landscape today, which is becoming fairly popular, people are coding in Ruby on Rails, Grails, and many other, in JavaScript, of course, and PHP, and many of the dynamic languages are typically smaller than static languages because of the fact that they offer certain features that static languages don't. Again, requires sort of performant architectures and scalable deployment and so on and so forth. So in the end, if you want to build a successful Web 2.0 application that services millions of users, technology-wise, from a rich web user interface perspective, there's several presentations today that will cover myriad technologies from a user interface standpoint. My presentation is going to focus on the back-end deployment in terms of how you're going to take that application and create an architecture that will basically offer zero downtime and scale to infinite transactions. So what are the variables that you're looking at considering in any typical application? There's scalability, which essentially is that, how much can my application serve or how much can my deployment serve? How many users, how many transactions, etc. There's performance, which is, sometimes confused with scalability, which is actually different from scalability in terms of performance talks about optimal utilization of resources. So how performant is my application? How well is it utilizing the CPU? How well is it utilizing the memory? How well is it performing? An application can be scalable, but may not actually be making optimal utilization of resources. Responsiveness, of course, is very important in a Web 2.0 landscape today. User experience is something that's crucial and critical. And so how responsive is your application? Availability is all about, at any given point in time, what's the probability that your application will be up? Uptime is probably one variable to measure availability. Downtime impact. Again, I'm trying to sort of cover these variables because when we start architecting the solution, we get to the practical portion of the presentation, we're actually going to look at each of these and make sure that our architecture or the deployment that we have satisfies all these requirements to the extent that we want to. Downtime impact is something, again, some people at times when building an application don't consider. Downtime impact is about how is the downtime going to impact your users? How many users are going to impact? For instance, one of the typical elements we speak about is don't put too many eggs in one basket. Because if you put too many, suppose for instance I have one monolithic server which serves 1 million users, if that server goes down, or if that architecture goes down, then essentially I'm inconveniencing a million users as compared to dividing my eggs across multiple different baskets. So when you talk about downtime impact, we're talking about what's the impact on the user. What is the type of impact on the user? If the downtime user is just going to not get the service, or is he going to lose data, or is there going to be some other implication of the downtime? So that's something that's important to consider when you're building an application. Obviously, cost is a crucial factor when it comes to building any architecture or environment. And lastly, maintenance effort. Now, you can build a really complex design that offers zero downtime, can scale infinitely, but if it's very difficult to maintain, then obviously it doesn't, doesn't give us any benefits. So what we want, if you look at the variables, we want high scalability, availability, performance, and responsiveness. And we want low downtime impact, cost, and maintenance effort. So that's what we're going to cover today. So the factors, so we spoke about the variables in terms of what we want. Now, what are the factors that influence these variables? And this is by no means a comprehensive list, but you're talking about platform selection, hardware, actual application design, the deployment architecture, what kind of monitoring you have in place. All of these factors can influence the variables that we're looking at. And we'll be covering some of these today. This presentation is not going to cover all of them, but just wanted to give you guys a brief preview. So let's start, all right? What we're going to do is we're going to start building an example architecture for an example application. I haven't specified any specific application. We're just going to start with a simplistic application. And what we're going to do is we're going to build it up in terms of scaling in iterative incremental steps. So we'll start with a very simplistic configuration, and we'll keep adding on components to it and changing the architecture. The way we'll be doing this, and this is an interesting sort of step-by-step process that subconsciously everybody uses when they're creating a scalable architecture. We inspect the current architecture, we identify scalability bottlenecks, single points of failures, SPOF. Basically, if there's any particular for high availability, we need to make sure there's no single point of failure in the architecture. So we identify SPOFs, we identify availability issues, identify downtime impact risk zones, and after having identified one or more of the above in the existing architecture, we apply vertical scaling, vertical partitioning, horizontal scaling, horizontal partitioning, and we repeat the process. We once again go back and inspect the architecture, and we repeat the whole process once again. So let's start with what most applications look like. They look like a single box when you start off, when you deploy your application the first time. All applications today typically consist of an application server, or an application that's deployed on an app server or a web server. That's Tomcat, Resin. For Java, for PHP, you've got Apache with the PHP engine or whatever. But an app server and then a backend database server. And typically, when you deploy your app for the first time, you don't have any user, and you're still not venture funded. You'll most likely put both of them on the same box and start with an app server and a web server, app server and a DB server on a single machine. Now, the first step that we take to scale this upwards is to take that single box and, now you suddenly have thousands of users or 100 users or 500 users that are accessing your application. You're going to add more CPU, you're going to add more RAM, and that's what we refer to as vertical scaling. So vertical scaling is increasing the hardware resources without changing the number of nodes. I've still got one node, and inside that node, I'm essentially adding more and more CPU and more RAM, so it can service more users. But until what extent can I keep doing this? Well, some of you might say we can buy a 64-way, Sun processor-based machine. I mean, it's going to cost more than a Ferrari Enzo, then your manager is not going to be pretty happy about this. So how long can we continue doing this? So that's where we look at some of the advantages, disadvantages. Advantages are very simple to implement. All I have to do is upgrade the box. But the disadvantage is, one, there's a finite limit. There's a certain limit to which I can go. The hardware does not scale linearly. So, if I have one CPU, I add a second CPU, that does not mean I'm going to double the performance. There's actually a performance penalty. Each time you incrementally increase and upgrade that machine, there's going to be a performance penalty which keeps increasing. And so at some point in time, you're going to have diminishing returns. So upgrading that box by adding additional CPU, RAM, or capacity is not going to actually serve your purpose. It's going to actually diminish your returns. Of course, it requires downtime. If I'm upgrading the box, I need to bring down that box, change the hardware, and then put it back up. It's something that we don't really want to do because it's compromising on our high availability requirement. Increases downtime impact, obviously because of the fact there's a downtime, the number of users that are going to be accessing this particular box are all not going to be able to get access that particular service, and incremental costs increase exponentially. A 2-processor box is not double the cost of a single processor box, it's more than that. If I look at a 64-way machine, it's actually more costly than 64 independent machines. So the incremental cost is higher. So that's where we get to the next technique, which is vertical partitioning by services. So now what I did is I actually separated out the app server and the DB server into 2 separate boxes. So that's what vertical partitioning essentially means, is deploying each service on a separate node. So I take each service that's there. Right now my service consists of an app server and a database server. It could consist of a mail server, could consist of various different modules or services, and I can take each of them and deploy them onto separate boxes. The moment I did that, I've essentially increased my scalability. I've essentially increased the number of users that I can serve. So I've increased per application availability. What this means is, in this particular case, it might not be that apparent, because if my DB server goes down, then my application probably is down. If my app server goes down, then my application is probably down. But let's assume that my application also consisted of let's say if I've got Flickr, if I'm building Flickr, if I'm building Twitter, and one of the things that I do is mail notification. So each time somebody puts a post, I send out an email to notify all the users, right? So that requires a mail server. Now I can put the mail server in a separate box, and if that mail server goes down, that does not mean the rest of my application goes down, right? It's just the mail server component that's gone down. So it's actually increasing my per application availability. The interesting thing about this vertical partitioning is it allows task-based specialization and tuning. Everybody here, most of you know that tuning a web server is very different from tuning a database server. A database server typically requires more RAM, a web server typically requires more processing capacity. A web server is always going to service large number of socket connections, therefore TCP/IP optimization and your kernel settings, etc., will be significantly different from what a database server would be, significantly different from how a database server would be tuned. So when you had all of these in one box, all these services on one box, you couldn't actually tune that box to specifically cater to the requirements of that particular function. But now when I vertically partition by service, I'm able to optimize and tune each box for the task that it is performing. Reduces context switching, simple to implement for out-of-band processes. What I mean by out-of-band processes, the moment I have multiple servers, now here I'm not talking about the physical server, but an application server, a database server, etc. It's actually a very simple process to just pick up the database server and drop it into another box. So the moment I'm looking at 2 things that have a process boundary, 2 components or 2 modules that have a separate process boundary, they're running in separate processes, very simple to separate them or vertically partition them. It requires no changes to the application and the flexibility increases. Negative is suboptimal resource utilization, which means that it is possible in this architecture that my database server is very underutilized. The CPU is never peaking, etc. My web server, CPU is always peaking, etc. So because I've separated or vertically partitioned my services, it might so happen that in the different boxes that I actually have suboptimal resource utilization in some circumstances. So now, the term vertical partitioning, important thing out here, denotes taking services. So actually think about it as, I've got service 1, service 2, service 3. I'm just drawing a vertical line and taking each of them and moving to a separate unit, a separate node or a separate server. And it can be performed at various layers. So you can do it at the app layer, at the server layer, at the data layer, at the hardware layer. And I'll talk about some of this going forward. Each node, each separate slice that you create is performing a separate task. So here, our verticals, when I looked at vertical scaling, I had a single node and I was upgrading its hardware. When I look at vertical partitioning, I'm dividing now my application across nodes, but they're heterogeneous nodes, which means each node is actually performing an independent task or functionality. Now, we move ahead so as I said, again, this is a finite scalability, right? Because now I've finished moving my app server and my DB server into 2 separate boxes. After 1,000, I reach 2,000 users, my application cannot take it anymore. So what's the next step? So I move to horizontal scaling. Where typically most people, you'll always, when you start off with an application, you'll typically go through this general route of scaling. You move your app server and DB server into 2 separate boxes. And the next step that you'll typically take is to start scaling your app server. Because that's the one that's taking all the user requests, all the user connections and performing all the computations, etc. So the typical process to do this is to take a load balancer, deploy the same copy of your app server across, multiple nodes, and load balance it through a load balancer. This is typically referred to as scaling out an application. In case of vertical scaling, you refer to it as scaling up a server. Here you refer to it as scaling out an app server. Now, let's first, before we get to details on load balancing, etc., let's understand the term horizontal scaling. In horizontal scaling, I'm increasing the number of nodes, but now there are homogeneous nodes. So in the previous scenario, on vertical partitioning, I basically partitioned my application across multiple servers, and they were heterogeneous nodes. Out here, there are homogeneous nodes, meaning every node has got the same copy of the app server. Each node performs the same tasks and is identical. Again, can be performed for any particular type of node, such as an app server and a DB server. We'll talk about how we do this for a database going forward. So when we look at load balancing, so I want to spend some time on horizontal scaling because now we're starting to get into something that's slightly more complex as a deployment. When I'm horizontally scaling my app server, I need a load balancer. A load balancer essentially performs the task of dividing the load across the 3 different app servers that you saw in the diagram. So there are certain considerations in terms of how I can load balance my app server. And I'm going to go through several slides that explain each of these considerations. Firstly, whether to go for a hardware load balancer or a software load balancer. A hardware load balancer is invariably faster. A software load balancer is typically more configurable, though these days hardware load balancers actually come with significant... okay, I have to make a quick announcement, so there are t-shirts going to be distributed outside after the session. Getting back to the session. Software, but these days hardware load balancers are also quite customizable. In fact, almost equivalently customizable as a software load balancer. They actually give you more bang for the buck. Hardware load balancers these days are actually fairly cheap and can service millions and millions of requests and therefore actually give you more bang for the buck as compared to software load balancers. And typically load balance is also combined with something called HTTP acceleration, which I'll talk about, reverse proxying or HTTP acceleration. I've got a slide on that at the ending, so I'll talk about that real quick at that point in time. The next thing that you want to look at when you're load balancing your app server is how you're going to perform your session management. And there are various options in terms of how you perform your session management. One option is called sticky sessions. Sticky sessions refers to how many people here have heard of sticky sessions? So sticky sessions, so fair amount of you knows, refers to a fact that when a user, a typical load balancer, the way it balances load is each time it gets a request, it needs to determine which machine to send it to. And there are various algorithms that it can run. It can do this in round robin. It can do this in least utilization. So it actually figures out which machine has got the lowest utilization right now and send the request to that machine and so on and so forth. Sticky sessions adds sort of a element to that algorithm in the sense that when a user starts a session with your app server, the first time he starts, the first request the user sends, he'll be sent to one particular node. And then all subsequent requests of that user will be sent to the same node that was selected for the first request. The advantage of this is that that particular app server has already loaded that user's session and so on and so forth. And then it doesn't require any shared session store. And I'll come to that. But people understand HTTP is a stateless protocol, right? So you need, basically you use, cookies or HTTP URL rewriting, etc. for session management, where essentially you maintain a session store for each user. Now, if a user's request goes to app server 1 and the next request of that user goes to app server 2, how does app server 2 fetch the session data that was created in app server 1? So and there are various ways to do this. One of the ways of session management, as I said, is sticky sessions, where if each subsequent request is, then there's absolutely no issue because that particular node will have that session. Of course, the unfortunate thing out here is if that particular server goes, then all the users that were connected to that particular server now, unfortunately, lose their entire session. If their next request goes to any of the other app servers, then the session data is not available. They have to re-log in. And if there's any important data in the session, like if they filled up a shopping cart with 20 items, they're essentially going to lose their entire shopping cart. The other issue with sticky sessions is invariably, it ends up creating an asymmetric load distribution. Because sticky sessions, you cannot guarantee that all your servers are equally utilized at all points in time, because there might be a certain set of users who happen to coincidentally land on one machine, who are the heavy users, and the light users happen to land on the other machine. Or in case of a downtime, this is where the issue sort of compounds. If one of the servers goes down, then all the subsequent user sessions are going to go on the other two machines. Then when this machine comes up, you'll find that this particular machine, which has just come up, is going to have relatively lesser load or relatively lesser utilization than the other two machines, because the fact that now all the user requests that happen to come to the load balancer within that 1 hour downtime, let's say, are all going to the first two or the two machines that were up at that point in time. So another alternative to sticky sessions is what's called central session storage, where instead of each app server storing a user session in memory, you actually have a central storage. It could be an NFS mount, or it could be an RDBMS. Most circumstances, you typically use an RDBMS like a MySQL database or a MS SQL database or a Postgres database or whatever. And each application stores its session in that central session store. And now this is completely stateless, which means the load balancer doesn't really care where the request goes. It could send the request to any app server. Each time the app server gets a request, it loads the session data from the central session store and has the session data accessible to it at all points in time. Of course, this automatically means that in the previous situation, there was no central session store. Here now we have two problems. One is that we've automatically created a single point of failure. If my central session store dies, it goes down, all three app servers don't have a session store, so the application is down. Which means I have to now do something about that session store. And the second thing is that there's additional disk and network I/O of some form or the other each time the session is being accessed. So each time the session is being read, it's being read from the database. Each time the session is being written to, it's being written to a database. And it involves, assuming the session store is deployed on a separate box that's accessible to all three machines, it involves a network call, it involves a SQL transaction, it involves a database write, it involves a disk I/O, etc., which obviously increases latency. But again, all of this honestly is very marginal, so you don't really need to bother about it, worry about it to that much of an extent, but it's just an element that you need to consider. The third technique is called clustered session management. And clustered session management, instead of having a central session store, what ends up happening is all the app servers use a common protocol to communicate with each other to replicate the session data. So each time, so instead of now managing the data, this is more of if people are familiar, the earlier topology was a centralized topology. This is a P2P topology, a peer-to-peer topology, where every app servers appear. Whenever a session is created, it immediately broadcasts a message to the other app server saying as a new user session created. Whenever any of them changes the session, it again broadcasts a message to all of them saying, look, this session has changed, this is a new data, so on and so forth. Or data gets deleted from a session or session expires, etc. All of it is done through mutual arbitration, through mutual message passing between the servers. Now, there's some advantages and disadvantages again. The advantage is that there's no central session store, and I still achieve statelessness, which means I can send any request to any particular server. The disadvantage is that the message passing between each of the servers, the number of messages required exponentially increases with every new node that I add. So every time I add one more node, now messages have to be broadcast to all the nodes each time the session changes. So very quickly, you can start having a lot of data transfer and data traffic happening between every one of the servers. In rare scenarios, which doesn't really happen too often or doesn't really happen in most circumstances, but rare scenarios, you can also find a situation where hypothetically a user request reached an app server before a message reached an app server, and therefore the app server may actually have stale session data. So user's first request went to app server 1, and user immediately sent out a second request because he's got a multi-threaded client that's actually fairly fast on the client side. And before the app server 1 could send out that session information to app server 10, the user's second request reached app server 10, and the session was not available, and therefore the user basically got a login form. So again, that's depending on if a user is a regular browsing user, it's a very low chance that a setup inside a controlled LAN environment will actually take longer time to pass a message than a user's request coming from far away. But if a user actually has an application that's sending requests very rapidly or is an automated application on the client side, it is actually possible. So it's something that you need to consider. Of course, you can combine them. And again, I just want to make sure that everybody's acquainted with all the different approaches. So I can actually have sticky sessions with a central session store. Or I can have sticky sessions with clustered session management. So I can actually combine sticky sessions with any one of the other two approaches. And so in sticky sessions with central session store, I get the advantages of a central session store, which means that, I have the ability to, if I'm using sticky sessions, I'm not getting the statelessness, but I have a central session store that's accessible to all the machines. So if machine 1 goes down, then machine 2, machine 3 can still serve that user's request. But I also have the advantage of sticky sessions, which means that each time the user's request is still going to machine number 1. So now reads of the sessions do not need to go to the database each time. So because I combined sticky session and central session store, reads of session do not generate network I/O or disk I/O. Only writes to a session generate network I/O and disk I/O. So again, you can play around with these combinations and figure out what's most appropriate for your application. Typically, based on our experience, the kind of applications that we've built, what I would recommend is, if you have a small number of app servers, clustered session management is fairly easy to set up. But again, remember, this is only for a standard browser user browsing your application at normal speeds kind of a scenario. In any other scenario, you might have those situations where a user doesn't get session data. But it's very easy to set up because you don't have to set up any central session store. You don't have to manage an additional RDBMS. You don't have to set up, configure, and optimize another machine. But ideal circumstances, I would recommend using a central session store and use sticky sessions only if you have to. It doesn't really give a dramatic advantage. And in fact, one of the advantages that we spoke about in terms of sticky sessions right now is that my app server, after the first request, doesn't have to keep going back to the database to read back the session. But you can actually achieve that same advantage by using caching by creating an L1 cache and L2 cache along with the central session store. I'll talk about that in a slide going forward. So ideal circumstances, what I would recommend is a central session store. Don't really bother with sticky sessions unless you really have to. And it's a fairly simplistic approach. All you have to do is deploy a central database that all your app servers can talk to. So we spoke about session management. We spoke about load balancing, selecting a load balancer. Now let's talk about the element that I spoke about when we started with load balancing, which is the load balancer now. Now the moment I have 3 app servers and 1 load balancer, I have a single point of failure, which is the load balancer itself. So the load balancer goes down. It doesn't matter if I have 50 application servers behind it. My application is not going to be available. So typically, most load balancers will support either an active-passive or an active-active sort of a fallback scenario, right? So you can configure 2 hardware load balancers or daisy chain, 3 hardware or multiple hardware load balancers. Or even in software, you can actually have multiple software load balancers serve as a single load balancer, appear as a single load balancer to the external world, so that if one of the load balancer goes down, the other one takes over. The names are self-explanatory. The active-passive means that one load balancer is just standing out there passively. It's not really doing anything. More in the active load balancer, if it goes down, the passive load balancer has got a heartbeat with the active load balancer, detects that, automatically takes up the assignment of the IP address and so on and so forth, and starts performing the task the active one was performing. In an active-active scenario, both the load balancers are active. Now, typically the way this is done, active-active setup is slightly more complex. If you actually start out with this, I would suggest you start out with an active-passive deployment and then move to an active-active one. But in active-active, typically the way this will work is one load balancer will be serving X number of app servers, another load balancer will be serving X number of app servers, and both will be configured to take over the other load balancer's load in case it goes down. Now, the thing to remember about active-active load balancer is that it's not going to work if both of them are actually at peak utilization, right? If both the load balancers are actually 100% utilization, the one of them goes down, the other one's now going to have to take up 200% of the load. It's obviously not going to work. So the only scenario where it can work is there at 50% utilization, which means, really speaking, you have a very similar situation to an active-passive. Of course, the only scenario where active-active can actually give you cost, the only reason to do active-active is cost benefits. Otherwise, you'd go active-passive. The only scenario where active-active can help is when your load balancers that are being daisy chained are not 2 or 3, but more than that in number. So if you have 4 load balancers or 5 load balancers, you go the active-active route, you still get a cost advantage because of the fact that you don't have to double up your resources. You don't have to do a 2N type of an architecture. So that's basically as far as eliminating the load balancer single point of failure is concerned. So at the end of horizontal scaling, which is what we were talking about before we rattled off into load balancers and session management, this is what now, previously we had one app server, 1 DB server. Now this is what our architecture looks like. This particular box represents my web cluster, which consists of 2 load balancers and 3 app server nodes, and all of them are talking to a DB server. So at the end of step 4, after I horizontally scaled, I've increased my availability because I've got multiple web servers, any app servers, any of them can go down and my application still survives. My load balancer can go down, my application still survives. I haven't yet made any changes to the application. It's all at my deployment level. Okay, fairly easy to set up. But again, this has finite scalability for a couple of reasons. One is I can't infinitely scale this. I can't have hundreds and thousands of app servers behind a bunch of load balancers. And 2, I still have to tackle this guy out here. My DB server. Now, typically at this point, this is exactly how your application will move. You'll start off by scaling out your web servers, your app servers. You'll have multiple app servers. You'll have one database server. And now you're going to start facing bottleneck or scalability issues at your DB server level. My DB server is a single point of failure and also a scalability bottleneck in this particular scenario. So now we'll apply once again vertical partitioning. Earlier we did vertical partitioning at the services layer. So we divided our two services, app server and database server, into two separate boxes. Now we're going to actually do it at the storage layer. So we actually separate out some functionality from my DB server and move it into a SAN. And this is, honestly, before you start considering, most people start off with thinking about clustering my database and replication and so on and so forth. This one simple step first automatically provides you a significant boost in terms of performance for almost any given application. Most circumstances you'll find, people, take some time to actually size up your application or your server. You'll actually find, most people will find, oh, my DB server is peaking, the load average is very high, etc. And you start adding CPU, start adding RAM, but it doesn't change anything. It doesn't actually really increase your performance. Your load average still continues to be high. The reason for that is it's not CPU or RAM that's actually being consumed out there that's actually causing the problem. It's disk IO. And you'll actually notice if you check out your CPU states, your CPU utilization might be, your load average might be high, but your CPU is actually on IO wait at all points in time. And it's actually because of the fact that your disk can't keep up with the CPU. So first step that you typically end up taking is move your data into a SAN. So you got a storage area network with one or more SAN devices, each of which have, 8, 16, 24, 48 hard drives, and they can churn out data at extremely rapid speeds. So now you once again are able to consume your CPU, you utilize your CPU to the fullest extent, and you get higher performance basically. So boost performance of the DB server, of course, increases costs, but SANs again are pretty cheap these days. You can actually build one on your own, but even buying a standard regular SAN device is not fairly expensive these days. The SAN side, this purple little box, which I'm not going to expand on, is the science by itself. Literally, when you look at storage management, there are hundreds and hundreds of different possible configurations and so many different things that you can do with storage in terms of optimization, what kind of hard drive to select, what kind of SAN protocol to select, ISCA-Z, FC, SAS, etc., and things like that. And that by itself is a fairly lengthy dialogue. I've actually got a presentation up on wiki.directeye.com. It's a presentation I'd conducted in one of the other seminars, which talks about storage specifically and only storage in terms of how to build scalable storage solutions. So you can actually refer that if you go to that URL. But this presentation is going to cover more of the application architecture rather than the storage architecture. So once I finish vertically partitioning, my next bottleneck is again going to be DB server, because my app servers I can keep scaling. I can keep adding app servers. Okay. At the SAN side, I can actually keep scaling my storage area network also. And again, like I said, it's a science by itself. So details can you can refer some of the stuff that's available online for that. But my bottleneck is again going to become this little guy out here. It's my database server. So we go to step 6, which is horizontal scaling for the database. This is where we start talking about replication, clustering, etc., and things like that. Essentially, the same horizontal scaling that I did for my web servers. What did I talk about when I said horizontal scaling for my web servers? Homogeneous nodes. Each node performs the same task and same function, right? And essentially sitting behind a load balancer so that all web servers appear together as the terminology used for this. Actually, the word cluster is the most misused term in deployment architectures. But the terminology used for this is a cluster of servers, a cluster which essentially appears as one unit to the external world. So theoretically, it appears as one single machine, but internally it's actually multiple different machines acting as one. So it's a homogeneous cluster, and we managed to do that for our app servers. Now let's look at how we're going to do that for our database. On the database side, we have two options for creating a homogeneous cluster, or for scaling out our database, or for horizontally scaling our database. All three mean the same. When I say horizontally scaling the database server, I mean that I want to multiply one database server node into multiple database server nodes, each of which perform the same task. So when my app server talks to the database servers, it is talking to one unit as if it's one database server, but actually underlying it are multiple nodes. So two options that I have is a shared nothing cluster or a real application cluster, which is also called a shared storage cluster because the storage out there is shared. Let's first look at shared nothing clusters. Shared nothing cluster essentially is nothing but taking my database server, which is one database server, and instead of that deploying 3 or 5 or how many ever I need for my application, or 2 to start with, and essentially they share nothing. They're actually independent nodes. In fact, if I go back to our web server horizontal scaling, by the way, when I go back to my web server horizontal scaling, the sticky sessions diagram or the clustered session management diagram that I showed to you was a shared nothing architecture out there. Because I had multiple web server, multiple app servers, and they weren't sharing anything. They were all independent. They were all independently handling requests. When I look at my central session store architecture in my app server horizontal scaling, that was actually a shared architecture. It wasn't a shared nothing architecture. It actually, multiple app servers were sharing a single central session store. So just to clarify the term shared nothing out here, when I look at shared nothing, so now coming back to a database context, when I look at a shared nothing architecture for databases, it essentially means multiple database server nodes which are sharing nothing. Each of them has a complete copy of the database. They're identical in terms of the fact that each of them can handle, well, they're almost identical, and I'll get to that shortly, but they can all handle requests from the app servers, and they don't share any hardware or architecture. This is achieved through database replication. Again, the database replication part could be done at any level. It could be done at the RDBMS level if the RDBMS natively supports it, or there are drivers and proxies available through which your app server can talk to. Again, it doesn't require too much modification of your application code, but these proxies or drivers will handle all of the replication bits, so they'll actually talk to multiple databases. The app server will assume, since they're talking to a database driver or a proxy, that they're talking to one single database only. Okay, note here, however, that, when I talk about these three, the actual database file may be stored on a SAN. It could be a central SAN. That does not make this a shared architecture. The SAN is actually a separate physical device. It could be same set of 16 hard drives. There are 3 partitions. One partition is being used by DB server 1, one partition by DB server 2, and one partition by DB server 3. But all 3 of them have their independent database files. All 3 of them are replicas. Now, if you look at replication in shared nothing architecture, again, just like we went through horizontal scaling, we went through various considerations. If you choose a shared nothing database cluster, there are various considerations when it comes to replication. Let's look at those considerations. First, if I have 3 database servers, I can choose a master-slave arrangement or a multi-master arrangement. Terminology itself makes it clear. A master-slave arrangement is one master or a certain number of masters, and these masters essentially, typically one master. This master essentially is where all the write operations are performed. This master is in turn responsible for replicating out all the changes to independent slave nodes. Slave nodes and read operations can be performed across the master or the slaves. Write operations are performed only to one master. Multi-master scenarios where you can write to any of the databases and it will replicate out the changes to all the other database nodes that exist. A multi-master scenario is typically always more complicated because there's a conflict possibility. In a single master-slave scenario, since all writes are going to one master, there's no conflict possibility. But if you have multi-master and the same row is modified at the same time in 2 different masters, then when they're cross-replicating, you now have a need for conflict resolution, which can be specified either as an automated set of rules, or there'll have to be a manual intervention at that point in time to actually resolve that conflict. In most circumstances, I would say pretty much all circumstances, you'll never need multi-master. You'll typically always look at replication from a master-slave perspective. You'll always have one master with a set of cascaded slaves. And again, out here you can cascade slaves. So you can have one master replicating out to 5 slaves, which in turn are each replicating out to another 2 slaves each, and so on. So you can set up your replication architecture in the most convenient fashion possible. The next element to consider when you're looking at replicating, so one element was either multi-master or master-slave. I would recommend we go master-slave. The next element to consider is, do you want to do asynchronous replication or synchronous replication? Asynchronous replication means that a master receives a write. The moment it finishes writing to its own copy, it returns a response to the client saying that, everything done. Then it is responsible for replicating that change out to all the slaves. It guarantees that replication. It will make sure that it happens. But the response to the client is immediate, and the actual replication is performed asynchronously. In case of synchronous replication, on the other hand, the master will write to its own database and will also make sure that all the slaves write that change to their respective databases and only then return a response back to the client. So the change is actually made synchronously. And again, there are advantages and disadvantages and pros and cons in terms of scenarios and situations as to which architecture you choose. In the asynchronous replication, response to client is rapid. Client gets an immediate response. While in the synchronous replication situation, if you have 10 slaves and 1 master, then you actually have 10 modifications have to be made across all slaves. Actually, if you guys have heard of 2PC, it's a 2-phase commit process basically. Before a commit can be can be confirmed by that master. All the slaves need to have committed that particular data change, and only then will the master respond back to the client. Typically, so I'll tell you where what are the implications on your application. If you're using asynchronous replication or synchronous replication, your writes are always going to one single master in the master-slave scenario. Now let's talk about the reads. The reads are load balanced across all the, suppose I have 5 database servers, one of them is a master. If I want to, let's say it's an employee salary table. If I want to select, all employees salary in 10,000, right? Essentially, I can send that read query to any of the replicas or any of the 5 database servers and essentially get the response that I require. But there's a concept called critical reads. There are scenarios in your application where you can't afford, because the master is asynchronously replicating to a slave, there's a small chance that before the replication to the slave takes place, your application fires a second query to a slave and is actually getting stale information. In most circumstances like searches, web searches, basic lists, basic views, user profile views, etc., it's not going to make much of a difference. But the moment you get to important elements, important portions of your application, such as, for instance, if you're calculating, if you're salary for actually making a payroll entry, or if you're computing a person's bank balance, applications like those cannot afford to have stale data, because based on the data that they get, they're going to make certain decisions which are going to impact the integrity of the data itself. So you can't actually perform, for instance, if I withdraw $100 from my bank and immediately fire a query to withdraw another $100, and if that query goes to a slave which actually hasn't recorded the first transaction, I'll be allowed to withdraw a second $100, which is obviously not something that you can have in an application. So when you're looking at critical reads, they will need to be, critical reads can only be sent to those slaves which are as updated as the live master is. And again, you don't have to bother with all of this because your driver or your proxy or your DAO layer is going to take care of this. It will keep track of, where the commits are being made, what data is being written where, especially if you choose the right kind of software. But the idea now is that each time I send in a read request, that read request now cannot go to all of my nodes, it can only go to some of my nodes. Mind you, this is only for critical reads. So if your application doesn't have too many critical reads, easily go with asynchronous replication. There's firstly the chance of you getting stale data itself is rare. Once again, going back to our previous assertion that a bunch of database servers that are actually in the same LAN, same LAN segment, which is what typically your configuration is going to be, will end up passing data far more faster than receiving a subsequent request from a client. So most circumstances you won't run into that situation. And most applications getting data that's a few seconds, or in this case, a few microseconds or milliseconds stale is not going to make much of a difference to your application. So in most circumstances, async replication is going to suffice for you. But if you're looking at mission critical type of transactions where data integrity is very, very important, async replication can still work for you, but synchronous replication may be a better choice. The next consideration to make when you're looking at replication is should you look at replication at the RDBMS level or at the, well actually this is not really a consideration, this is part of a platform selection. If you select an RDBMS that supports replication, then that's the best solution because the database natively supports replication. It's going to be the quickest and most likely the most reliable solution for replication any which ways. If your RDBMS doesn't support replication, then there are various third-party tools which work at the DAO layer or the driver layer, which can actually provide replication for databases that don't support replication, like CJDBC, Sequoia, etc., that actually work on the driver layer and actually provide replication to RDBMSs that don't support it natively. Interesting thing about these kind of tools which work at the driver or DAO layer is unlike a native replication tool, they can actually support heterogeneous databases, which means I can actually have replications and where one of my node is an MS SQL server, another node is a Postgres database, the third node is a MySQL database. If I use native RDBMS replication, I can't do that because MS SQL is not going to replicate to a MySQL database. But if I use replication at the driver layer, then basically I can have heterogeneous databases. Now, of course, this is just an interesting piece of trivia. In most circumstances, you're not really going to actually have heterogeneous database nodes. The only known benefit that I have heard for having heterogeneous database nodes in your single horizontally scaled database cluster is that if there's a vulnerability discovered for MS SQL and your MS SQL server is compromised, then all your MS SQL servers won't get compromised because you have a heterogeneous database cluster. Most circumstances, your database cluster is going to be behind a DMZ or it's going to be in a separate subnet. It's not going to be directly accessible to anything except for your application servers behind a firewall. So the possibility of that, of a vulnerability type of a situation actually impacting your database cluster is significantly lower. And so I won't really count that as an advantage in most circumstances. I would say ideally choose an RDBMS that actually supports replication natively. That's the best way to perform replication as compared to trying to do it at the driver or DO layer. So that finishes replication and finishes a shared nothing cluster. When I started off with horizontal scaling, our goal was to take one database node and convert it to multiple database nodes such that all of them act as one. The two ways of doing that was, one was a shared nothing cluster, and the second way is called a real application cluster. This is actually true clustering. Right now, I think the only database that supports this is Oracle, and I believe MS SQL will start supporting it soon, but as of right now, Oracle is the only database that I know that supports a real application cluster. And essentially, a real application cluster, you have your database as a software installed on multiple nodes, all talking to a common single storage file or a single storage partition. So in a shared nothing cluster, each database node had its own copy of that database. In a real application cluster, each database node is talking to one single database. There's only one copy of the database now. It's on a SAN, so it's all redundant and high available and all that stuff. But it's only a single copy of the database, and all these database servers are talking to that one single copy. Right? File system needs to be a clustered file system to support this. So you have Red Hat GFS, or Oracle has its own file system called OFS. Both of these file systems actually support the Oracle Real Application Cluster. I'm putting this here primarily for academic purposes. Last I checked, this is a hopelessly expensive solution, and a shared nothing cluster is going to actually work equally well, or in fact, as is argued, and there are some white papers available for this, in many cases even better. And again, I'm not going to sit and argue about the merits and demerits. There are scenarios where a real application cluster may actually perform better than a shared nothing cluster and vice versa, but for all practical purposes, both of them will work for you. A shared nothing cluster created out of PostgreSQL and MySQL costs you nothing. Oracle Real Application Cluster is actually going to be fairly expensive as an exercise. So my recommendation is, try and choose. I'm getting used to this actually. I just bought this a couple of days ago. But my recommendation is that try and choose a database which supports master-slave replication. Typically use asynchronous replication because synchronous is not required. It'll slow down your application further because latency will increase. Write your DAO layer to ensure that writes are sent to a single DB. So this actually shows you the architecture. Writes are sent to this one master, okay? And even critical reads, if your application has any, are typically sent to the master, okay? And all the reads are load balanced between any of them. So reads are sent to all three. Actually, there should have been one more red arrow out here. But reads can be sent to any of them, and writes are sent to one master, which replicates out to the other nodes. So this is our this is our final architecture at step 6. After I've horizontally scaled the database, I've essentially got multiple web servers behind multiple app servers behind a load balancer talking to a cluster of databases, which is talking to a SAN. And I've actually shown 3 separate partitions out here just to signify my recommendation of going for a shared nothing cluster. If this was a real application cluster, then the SAN would actually only have one single partition to which the DB cluster talks to. So now, my database server is no longer a single point of failure, right? Any one of these database server nodes can go down, no problem. A SAN by itself is redundant, and in fact, I can actually have multiple SAN devices inside the SAN. So there's ample redundancy here, ample redundancy here, and ample redundancy here, which means now my application is highly available. There's no single point of failure, and it's fairly scalable. I can keep adding web nodes and I can keep adding DB nodes, but it still has a finite limit. I can't keep adding DB nodes unto infinity, and I can't keep adding web nodes unto infinity. And let's look at the database side, because that's the one that's going to give out first. In fact, you'll actually be able to keep adding app servers fairly rapidly as your user base increases. But where you'll start again facing the bottleneck is eventually you'll reach a level where your shared nothing DB cluster is going to give away. And why is that? Let's actually quickly explore. A shared nothing cluster as a database cluster has a finite scaling limit. So I've taken an example out here. Let's say your application, the ratio of reads to writes is 2:1, which is, I mean, in fact, in most applications, it'll actually be much more than this. The reason why a shared nothing database cluster works is because you always have more reads than writes to most databases and most OLTP applications. Okay, so your writes are all going to one database, replicated out to all of them, and your reads are being load balanced. It's being served by, so writes are actually, when I say going to one database, eventually going to all of them. All nodes are performing the writes, and only one of them is performing a read. So every read operation can be handled by any one of them. Now, if you have a scenario where your reads to write ratio is 2:1, if I have two databases, then each database is performing writes 50% of the time and reads 50% of the time. Because if I have, so let's just, I mean, I've given an example out here. If I have 8 reads, that essentially results in case of two databases, 8 reads, since it's 2:1, 8 reads means I have 4 writes. So all 4 writes are going to go to both the databases, but the 8 reads are going to be divided into 4 reads for this guy and 4 reads for this guy. So that means 50% of the time my database is doing writes and 50% of the time it's performing reads. The moment I need to add more database nodes, that ratio starts leaning towards the database nodes only performing writes more and more and performing, actually participating in reads lesser and lesser. So the moment I have 4 databases, I essentially have 20% of my time being devoted to reads and 80% of my time or something like that devoted to writes as far as each database node is concerned. You'll realize at some point in time, we'll reach a scenario where adding one more database node is going to give me very marginal increment in the total capacity that I can handle, just because the fact that every node has to handle all the writes. And then it's only the reads that can get load balanced, right? So at some point in time, the number of writes in my application will increase to such an extent that adding additional node is going to actually become futile, or it's going to give me very marginal advantage. Which is why we now move on to the next and probably relatively the most complex mechanism for scaling your application to the next level. And this I've got a couple of more steps after this, but this is pretty much the nirvana of scaling in terms of any web app or any online application architecture, which is vertical and horizontal partitioning of your database. Essentially, vertical and horizontal partitioning talks about taking inside your database. If I have got 20 tables, I just slice them, take 10 tables and move them to one database, and take 10 tables and move them to another database. Now each database in turn can become a cluster. So now I automatically increase my scaling finite limit because of the fact that I've divided my my tables vertically. And this can be done not just on tables, not just at the table level, it can also be done at the column level. So for instance, if I have a users table which has got 50 columns, I can divide it into 2 tables with 25 columns each and move one table off to another database. And therefore utilization, sometimes I might need only the first 25 columns, sometimes the second 25, and sometimes both. And again, depending on that, I'll have to essentially modify my application. Vertical. By the way, when I talk about this step 7, the reason why I say that it's complex is because now you will either have to if you come this far without accounting for this, you'll actually have to modify your application, or ideal circumstances take into account vertical or horizontal partitioning into the original design when you build the application. It still limits my scalability to a finite limit, all right? Which brings me to horizontal partitioning of a database. Horizontal partitioning, I mean, it's very easy to remember. Vertical partitioning is if I've got my tables, I just draw a vertical line and divide and take a set of tables and move it to another node. In horizontal partitioning, I'm taking a single table or all the tables actually in the application and slicing it horizontally by taking a set of rows and moving it into another database node or another database server. So you typically choose an entity, and this is very easy to understand psychologically. A very simple statement, for instance, is that if you have an application, what you're essentially saying, when you're horizontally partitioning your database, what you're saying is, here's my cluster number 1, okay, which has, let's say, 5 database nodes, and that's the max limit that I want to put in that particular cluster. This cluster is going to serve 1 million users. As soon as it's, as soon as 1 million users have registered and are working, etc. and things like that, I'm going to take the same table structure identically, create one more database cluster, and basically put the next 1 million users out there. So that's essentially what horizontal partitioning means. Each database cluster has identical tables. So if you look at the diagram, 2 clusters that are formed, all of them have the same 4 tables, serving 1 million users each. Application code or DAO driver or a proxy, no. So now again here, since I've divided my rows, the app servers will need to know where to send the query, right? Earlier, if I had only one database cluster, my app server would always create a pool of database connections to that one server and send all the queries there. But now I'll need to write a layer at my data access layer. I'll need to write some code that will figure out based on my query based on which user I'm querying for or what data I'm querying for, where to send that particular SQL query. One of the negatives of horizontal partitioning is that SQL unions must be performed within code. Well, you actually can do it at the database layer also. Some proxy scripts and databases actually support that. But basically what I'm trying to say is that if I want to take 50 users from database cluster 1 and 50 users from database cluster 2 and generate a report, I can now do a simple select star from this and generate a union of both of them. Because they're across databases, I'll actually have to select those rows and do a union in my code. What are the techniques that I can use for horizontal partitioning? There are various techniques. There's FCFS, which is first million users go on cluster 1, second million users go on cluster 2. There's a round robin, which is, user 1 goes here, user 2 goes here, user 3 goes here. There's least utilization, which is typically useful when you're actually scaling up. So you'll start out with one database cluster. The moment you reach, let's say, 50% utilization of that database cluster, you'll put in a second one. Now you want this one to fill up because it's less utilized than the first one. So you'll actually let this one fill up till they both come to 50. Maybe you'll put a third one. Maybe you'll let these scale up to 60% utilization, put a third one. So the least utilization algorithm will make sure that it divides your users. Again, I'm using users here as an example, okay? The entity that you choose to horizontally partition on is entirely up to you. It could be used, if I look at, for instance, a school management application, you could horizontally partition by schools, by teachers, by classrooms, by users, however you want to choose in your application. You'll typically choose one entity in most circumstances and essentially make sure that so it's essentially replicas of your database structure. They're all identical database structures across those servers, across those clusters, but each of them is serving a finite number of users. You could actually have a hash-based horizontal partitioning where a hashing function decides, you compute a hash and then you decide which particular cluster to send that particular row to. You could use a value-based method. So you say user IDs 1 to million will be stored in cluster 1, or all users whose names start with A to M will be stored on cluster 1. Again, there are many different techniques available for horizontal partitioning. You can decide which one you want to choose. Ideal circumstances, round robin and least use are very easy to implement and actually work for most circumstances. Now you have to understand that if you use except for hash-based and maybe even value-based, in all the other circumstances, while you have multiple clusters, each serving a set of users, you also need to have one global user lookup map, which contains your whichever entity you're partitioning by, it contains the entire list and which database cluster does that particular entity map to. Because your application server needs to use that map to be able to actually figure out which database cluster to send that particular query to. So this is what my setup would look like. I've got my app servers which talk to a lookup map to figure out where to send the database query. Then I've got 2 database clusters and they're talking to one storage area network which can consist of n number of SAN devices. One of the things to note, by the way, when I talk about horizontal partitioning and vertical partitioning here for scaling, it's not the same as table partitioning. That is, if you read your MS SQL manual or many of these database manuals, they talk about a concept of table partitioning. This is not table partitioning. Table partitioning is nothing but partitioning data across multiple tables within the same database on the same node. The only advantage that table partitioning gives you is that you can actually spread tables across multiple disks, and by spreading data across multiple tables, you're actually creating a natural sort of a clustered index so that you can, so for instance, all data for the month of January will be in the table January, all the data for the month of February will be in the month of February, table February, and so on and so forth. So basically this is not the same as table partitioning. It's quite different from table partitioning. We're actually talking about separate nodes out here. Now, the next thing so now at this stage, I've really finished creating a scalable architecture that can scale pretty much infinitely, because I can keep horizontally partitioning my database clusters, and I can keep adding web clusters that talk to others. So each cluster is going to deal with each database cluster is going to deal with a certain number of users. Let's say 1 million users in total. In fact, a logical way to organize this, and what typically is called sets, basically. What I do now, so what I typically do is now I take this and I'll call it one set, okay? And you know what I mean, instead of now talking about a scenario where I infinitely scale just one set, for easier manageability, I divide this into logical units, saying that one set, for me, one set that I deploy for my web application will cater to 10 million users, and typically it will consist of 3 database clusters, 2 web clusters, 4 or 5 load balancers, firewalls or whatever, and that becomes one single set. And the moment I reach 10 million users, instead of adding more database clusters or more app servers here, I just create another completely fresh set. Again, this goes in line with the philosophy. Looks like, which means I have each set consisting of app server clusters, database clusters, and storage area networks. There's a global redirector which is required because typically your user will access an application using a single URL, directi.com or whatever web service that you're providing. So google.com. So there has to be one global redirector which will determine which set to redirect that user to. Then inside that set, everything is essentially servicing that particular user's request. Some of the negatives of horizontal partitioning, and these are negatives that you unfortunately have to live with, because when you finally reach that millions of users and billions of page views, your architecture will look like this. It can't be any different from this. And so these are negatives that you're going to have to live with, is that aggregation of data across sets is complex. So if I want to generate a report consisting of data from here and data from here, I have to write special code for that. Users may need to be moved across sets if sizing is improper, and that requires migration and sort of adds complexities, etc. And global application settings and preferences need to be replicated across sets. Since the same application deployed here and the same application deployed here, you want the page to appear green across your entire application. If that's an application preference, you obviously need to manage it across all your sets and all your servers, etc. Again, these are elements that you need to consider or keep in mind. By step 8, you pretty much finished building an architecture that will scale. Couple of other things that I wanted to add are sort of more like a wish list or interesting things that you'd actually now want to do to try and optimize the performance or the utilization of each of the sets that you've created so that you reduce your costs. So you'd start with caching. The next step that you'll take once you've built this entire architecture, you'll try and put in caching wherever possible. And every time you're looking at a disk I/O taking place, you're increasing latency, reducing performance, and increasing CPU weight. The moment you add caching, decreasing performance. So the moment you add caching, you're increasing performance, you're decreasing latency, increasing responsiveness for your user, and actually optimally utilizing your architecture or infrastructure. So you can have object caches, you can have session caches. If you remember the central session data store I spoke about, where each time a user request comes in, it has to read that central session store and fetch that user's session data. If you actually cache that session data, that call to the database does not need to be made, and you actually have a higher performant application. API cache, page caches. Many applications can actually create page caches. Facebook does that, for instance. It caches all the widgets and pages that it creates. So if there's no change, they can just serve out a static page instead of actually having to recreate their entire page. Some of the software that we use for this is Memcached, is written by Dangasoft. It's a open source, freely available, platform independent, distributed memory cache. Fairly easy to integrate with any application. It's got client libraries and literally everything, Python, Java, etc., etc. Terracotta is a Java only open source cache. If you're writing a Java-based application, Terracotta may actually give you higher performance than memcached because you don't have to serialize, deserialize objects. Memcached actually stores them in its own serialized format, while Terracotta actually stores them as POJOs in a JVM. So the serialization, deserialization reduces. Plus, it supports L1 and L2 caching as compared to memcached being only one level cache. Again, caching by itself is a science. I mean, you could take an entire presentation on caching itself, so I'm not going to get into details of caching out here. You guys can research that on your own independently. Step 10 is adding a HTTP accelerator. If you're writing a web application, in most circumstances, you will gain significant performance advantages by adding either a hardware or a software-based HTTP accelerator in front of your app servers. Typically what in fact, HTTP accelerators and load balancers in most cases come as one combined application, either hardware or software. So you're actually getting both the advantages of both the functionalities in one single module. And typically a HTTP accelerator, they're actually known as HTTP accelerators, reverse proxies, load balancers, layer 7 devices, various different names. But intelligent ones will typically do the following. They'll redirect static content requests to a lighter server. In most cases, you'll be using an application server like Tomcat or Apache, where each process or the process itself is fairly heavy, or each thread is fairly heavy. So you don't want to use it to serve images and static content, etc. So you might want to put on the same box or on separate boxes one more a lighter web server like LightTPPD or any of those lighter web servers, and your reverse proxy or your HTTP accelerator will redirect static content requests to a lighter HTTP server. It will also cache content based on rules. So images that pass through the proxy, reverse proxy or through the HTTP accelerator will get cached. So next request does not need to hit your app servers. It can be served from the accelerator box itself. Uses asynchronous non-blocking I/O. Most web servers today, Apache, Tomcat now has started using async and I/O, but Apache and many other web servers actually don't use non-blocking I/O. They use blocking I/O, which actually slows them down, requires a greater number of threads to process incoming client connections, requiring larger amount of memory. Reverse proxy generally uses async NIO, async non-blocking IO, so this actually reduces memory requirements and actually reduces the number of connections, in fact, and so that's the next point. What will typically end up happening is that if there are 50,000 incoming user connections, the accelerator, the HTTP accelerator will probably only make 50 or 100 or 200 connections to your app server. Those will be HTTP 1.1 keep alive connections. So on the front end side, it's serving 50,000 user connections, but your app server is seeing only 100 socket connections or 200 socket connections, thus improving the performance or enhancing the performance or making the most of that app server box as compared to wasting resources on that particular box. Some of the solutions that are available, Nginx and Pearlbal are both open source, software-based, reverse proxy, load balancers, and HTTP accelerators that you can use. Of course, there are hardware ones available. Step 11, which is the last step that I'm covering in this particular series, is again, after you've done caching and HTTP acceleration, some of the other cool stuff that you'll typically do in an application, you'll use content delivery networks if you've got a global audience, like Akamai or any other CDN that can distribute your content. Latency, people don't realize across submarine cable or satellite is significant when you cross Atlantic, Pacific, etc. There's a significant amount of time consumed for data to flow through. If you use CDNs, you're reducing that latency and increasing responsiveness. IP anycasting is, allows intelligent load balancing by sending a user's request to the closest available node automatically through IP routing tables again. I'm not going to get into the details of that, but it's something that you can use for your application to increase responsiveness and increase redundancy, because IP anycasting automatically takes care of routing the packet to another destination if that particular server is not available. Async non-blocking IO, if possible for network for sure, but even for disk, there are libraries available that can give you async non-blocking IO. Incorporate a multi-layer caching strategy. So, L1 cache is in process with your app server, L2 cache is across a network boundary, and L3 cache is across a disk boundary or on disk. You can use grid computing. This is again not relevant for most applications actually, but there are some applications where you can actually gain advantages through grid computing and parallel processing across nodes. Quickly, just to cover some platform selection considerations, you're going to be spend some time in selecting your programming language and your RDBMS. to make sure that it allows you to perform all the architectural elements that I spoke about, and also is best and most relevant for your, best suited to your particular application. So, I mean, I've just put in three variables out here, but you're actually going to select programming languages, scripting languages, RDBMSs, caches, servers, application servers, operating systems. You're going to select a large number of different platforms, and each choice is going to have an impact on your flexibility and your performance and your scalability options and so on and so forth. So choose them with care. All the techniques that we learned today can be applied in any order. So, I covered them one by one. I've covered them in the path or the process in which you'll typically end up applying them, but they can actually be applied in any order. Some of the other tips that I want to speak about is horizontal partitioning and vertical partitioning of your database is something you should try and incorporate your design early on, because that is one of the things that will require dramatic changes to your application if you actually do that as the last thing in your scaling process. Loosely couple all modules, implement a RESTful architecture or whatever, and perform application sizing ongoingly to figure out which way to scale, identify bottlenecks, identify single point of failures, and so on and so forth. And that sort of culminates my presentation today. So thank you, and if you have any questions, then I'm available to answer them. Most of the presentation's goal was to actually cover application layer scaling and not layer 2, layer 3 devices like routers and switches, etc. Most routers and switches come with native support for mirroring, bridging, and having sort of N+1 redundancy built in, so I can actually have multiple switches, multiple routers at each step in my architecture, etc. And then I can handle during my network planning. It doesn't have any impact whatsoever on my application or application design or the way I code my application, etc. But it's obviously an important aspect. All of us have faced situations where we're trying to troubleshoot an application downtime only to figure out somebody pulled out a network cable from somewhere and the application went down. So clearly it's a critical piece and it is important.
Yeah, the other question is on vertical partitioning for databases, right? It might pose a constraint. For example, if your query is using 2-3 tables, you can't just push those tables across the database.
You can't. So you'll have to actually select, when you vertical partition across database, you have to select tables specifically such that they, in general, most people when they design applications, your applications are actually end up being a bunch of tightly integrated modules. In many circumstances, most modules don't even have interdependencies. You just end up tightly integrated into a single JVM instance because it's easy to code that way. Single package, you deploy it as a WAR file and just go ahead and upload into your app server. And so invariably what ends up happening is your database server becomes database becomes like a 600 table massive database, where in most circumstances you can divide them into units saying that look, these 20 tables never talk to the other 20 tables, or my application never needs to talk to both of them together, etc. So you can use that for vertical partitioning. So that's how you make that
similar sense. Challenge in horizontal partitioning is that if you have a lot of static data, then that has to go across all the servers, right? And if
yes, all configuration data has to go across all servers, or you can store it in one central server and that can become another cluster. So again, depends on how you want to architect it. And I would suggest the latter approach, because the fact that configuration data is loaded once, so you don't really need very performant architecture for that. But instead of having to replicate that data across all database clusters, you might as well have one separate database cluster just for global application data. Yeah.
This is more technical in nature. You mentioned Sequoia and CJDBC, and you also said that it's sometimes.
Actually, I don't think they're called either one of them now. They've been taken over by Continuant.
Yes, I think Sequoia is the open source version, yes, and Continuant is the commercial version. But you did also say that it's preferable in most cases to use the database's native clustering mechanism versus using a driver or a proxy solution. What are your thoughts on Continuant? Because it's primarily intended for MySQL. It started out as a MySQL clustering solution. And it seems like now that MySQL's its clustering implementation is maturing, what are the benefits of using a driver?
Again, Continuant talks about the benefits of having a heterogeneous database environment. So you can actually have multiple different databases. You can have a MySQL plus PostgreSQL database server in the same cluster. So you can have my preference, again, I would typically, I haven't worked, honestly, so I don't want to comment on Continuant's MySQL product. I haven't worked on it. I've worked on some work with CJDBC and Sequoia, but I personally always lean towards using a native replication engine as compared to an external one, just because the same guys have written it. It's typically more elaborate. Database replication is something that I want, critical reliability is critical, data integrity is critical, so I don't want any sort of a lacuna out there. So there's a greater degree of comfort level with sort of native replication. Native replication is also faster, and it supports it supports, for instance, when I look at synchronous replication, it starts becoming fairly complex to implement at a DAO or driver level as compared to native replication, where two-phase commit would be natively supported at the database layer itself. So ideal circumstances, if there's a mature clustering platform that's available, that's native to the database, that's doing it at the database layer, I would lean towards that as a choice rather than third-party tools. But having said that, we use Sloaney for PostgreSQL replication very successfully and haven't had any issues with it. It's a fairly mature product. PostgreSQL itself doesn't have any native replication, and Sloaney works fairly well using simplistic triggers and additional metadata columns that it adds to the database. So, again, it depends again on the platform or the database that you're using. If you have the liberty or the luxury of choosing it from the very beginning, then I would say start by choosing something that has some native support for replication. But again, I don't want to contradict myself there partly, but the thing is that PostgreSQL is a very good database. We actually use it very, very actively. If you start looking at database performance, etc., Postgres uses something called MVCC, which is multi-version concurrency control, while MySQL and MS SQL use something called locking and arbitration. So typically when you want transactional support in a database, you can either do it using locking or you can do it using MVCC. Oracle and Postgres have gone the MVCC route, and MySQL and MS SQL have gone the locking route. Though the latest version of MS SQL actually does have a flag that you can use to switch on MVCC. But again, depending on your application, I have found in most OLTP applications, MVCC is actually faster if you have a lot of scenarios of deadlocks possibly taking place or writes to the same database table, etc. MVCC is actually faster and better than locking and arbitration, and therefore Postgres might be an appropriate database or RDBMS choice, or Oracle might be an appropriate RDBMS choice for that particular scenario. You choose Postgres, in that case, you don't have native replication, but then you have Sloaney. So, like I said, all of these choices need to be made at the time when you're actually, making a platform selections, but you might be constrained by having to choose one particular RDBMS. Then you might have to look at third-party tools for replication.
Right, so when you're retrofitting or when you're trying to scale and you haven't really thought about clustering when you began the process, you would probably have to use something like Continuum to...
That is correct. Okay. And it is being used in production environment in many, many successful applications. So, they have a good product. It's not definitely something that works. Okay, cool, thanks. Yeah.
Partitioning, whatever horizontal, vertical you are doing. But say, take an example where I want to deploy my application for say 50 million users. But this logic saturates in terms of performance for say 200 users. Now, when I want to consider number of nodes, if I want to partition, number of nodes itself will become say 50,000 to say 1 lakh or something. So how do you think of architecting these kind of...
Well, first problem that I would solve before even looking at trying to figure out how to manage. There's no application where I would recommend managing 50,000 nodes for the kind of usage that you're talking about. So I would first try and solve that particular situation. So, answering to your second question, sizing is not a simple mathematics of dividing by the number of users or dividing by the number of transactions. In fact, in most circumstances, sizing becomes the biggest challenge and typically, invariably has to be done. You can do sizing pre-production, but typically will have to be done on a production live environment. So you'll actually see stuff happening, like tables, and then based on that, come to a sizing conclusion. Based on that, decide how I'm going to expand that cluster. So it's not a very simplistic aspect of course, once your application has been in production for long, if it does not have a fair amount of time, you'll get a reasonable sizing exercise yourself. You'll typically know in your mind that, okay, for me a set consists of 25 servers, 7 of which are database servers, 15 of which are web servers, 2 of them are for the session store. You'll actually have that set in your mind, and then all you have to do is each time you want to sort of expand from that point onwards, you just deploy one more set and you start registering users out there. But it takes a certain amount of live production environment time before you can actually get to that mental sizing exercise of, okay, I know what to do as far as expanding this application is concerned.
But still, there are applications, for example, multimedia applications, say if you want to do face recognition or something like that, their performance saturates for say 200 users or 500 users.
Well, if you're doing face recognition, this is not going to be a application that's available to 50 million users simultaneously on the internet. It's typically going to be either using the even if that is the case, then the complex part, which is the face recognition algorithm, will likely be run on the user's desktop rather than being run on the server side. You ideally would not look at doing the computation of that part on the.
If there's an requirement where I'm implementing some such a situation, where I'm deploying some such solution, so there's an algorithm part which saturates for say 200 or 500 users, and also I have to provide this particular functionality live for say 50 million users. There's a security, some solution is.
Well, if that's the case, then you have no choice. You have to deploy whatever 50,000 or 1 million or 1 lakh or 500,000 nodes or whatever. There's no real other choice if that's the business requirement, so to speak. Like I said, I would first try and tackle the problem of not having my application saturate at 200 users rather than try and tackle sort of deployment across a large number.
And as per your experience, I mean, suppose if these 50,000 nodes I have to handle, so managing a tree or, I mean, what should be a correct choice as per your experience? I mean, up to what depth?
That by itself, honestly, is a lengthy, I mean, there's so many things that you can do. Like you can use Puppet, which is a tool for configuration of simultaneous, X number of servers. There are various tools that you can use that allow you to manage servers simultaneously, upgrade servers simultaneously, patch servers simultaneously, etc., and things like that. But that sort of is the system administration realm more than the application design realm. But we can take that offline independently. Yeah.
Ajax and Java, J2E and all those technologies. You were mentioning about the application servers and all. I just want to get some of the suggestions from you. Like you were mentioning about Apache and Tomcat and all. What if if we go with JBoss and all? I mean, can we cache using JBoss cache and all caching mechanisms?
J2E by itself, has caching built in. In fact, J2E, the reason for J2E to exist, though these days, truth be told, with Spring, Hibernate, and ORM and MVCC frameworks, J2E is actually going out of fashion. But EJBs and objects are by default cached in a container like JBoss, etc., and things like that. So you have caching mechanisms built in out there. You don't even have to bother looking at alternatives. Again, without knowing your application, I can't comment on it. But these days, I would strongly recommend steering clear from J2E and moving more towards sort of POJOs with frameworks. Just because it sort of becomes easier to manage, it's more modular, easier to deploy, is more performant, etc., and things like that.
Yeah, but we use this Hibernate ORM, and it doesn't have a default caching and all.
Hibernate has caching by default.
We need to implement that.
Well, you need to implement that in the sense you need to configure it more than implement it. You don't have to write any code for caching in Hibernate. I, again, personal opinion, and this is something that I incessantly fight with my developers about now and then, I typically try and tell them not to use unless, in certain applications, Hibernate is very good. In certain applications, I prefer not to use Hibernate. Not because of caching limitations or anything like that. I think it does a wonderful job of caching, etc. But because I personally don't prefer a situation where an automated piece of code is writing my SQL queries, because then I can't hand tweak them. Well, Hibernate does allow that, but because it gives you a simple ORM interface, developers don't tend to look at the queries, and therefore many circumstances when you look at optimization, you'll end up with a scenario where it's actually the Hibernate query that's not fully optimized or giving you sort of the best result, etc. Though they're doing a fairly good job of that in terms of improving it and enhancing it, but just the fact that it abstracts that layer out, I prefer native SQL querying directly, etc. But then you can use an ORM like Ibatis, for instance, which actually gives you the flexibility of writing your own queries and gives you an ORM, so gives you an object view. And then, for a cache, you can actually implement Terracotta or Memcached, etc. for caching those objects.
Thank you.